For this demo, first we'll change the weight of our reviews application between its different versions. Then, we'll create some routing rules so that different users will see different versions of our application. To be able to change the weight of traffic between different versions of an app, first we need to define those versions. This can be done by using destination rules, as we've talked earlier. For this demo, we can use the default destination rules from our samples folder. Then, let's create our virtual service. This virtual service will be named Reviews, and it will be affecting Reviews host. Under the HTTP route section, we have created two different destinations. First is for subset v1, that is defined by a destination rule. Second is for subset v2, and that is also defined by a destination rule. And you can see there's a weight distribution by 75 to 25 here. These numbers always need to be 100 when summed up. We can apply this YAML now. Let's check with Analyze if it's all good. Yes, it's all looking good. Now, let's create some traffic to our application to see how this change in weight will affect it. Switching back to Kali for that, we can check the istio configs. Here are the destination rules we created from the samples folder. As you can see, there are three different subsets that will be matched by the services labels: version v1, v2, and v3. Let's check out Reviews virtual service. You can see the weight distribution in this bar on the right. Now, let's see the graph. As you can see, the weight of all review service is distributed between v1 and v2. When we go to the app, it shows that there is only a no star and a black star version. Red star version is v3 and it is not there. Now, let's stop the loop that we have the traffic coming from and try to feel the 75-25% difference in the browser. As you can see, version 1 is more common than version 2. I've just stopped the other traffic source, so the balance might not be very clear right now, but you can see the difference. Now, let's change our weight distribution once more, but this time we'll do this using the Kali interface. This time, I'm adding another destination, but I'm not changing any weight, so it will be 125 in total. Let's see how it will go. As you can see, Kali interface did not let me save this, and it has given me a proper error on the X at the top. Let's fix this weight distribution. And also I want another subset v3 here. So, as you can see, first we had only two versions of reviews, and we now, even for a small percentage of requests, introduced another version of it. We can check it in the browser, and it is not common, but we've started to see some red stars in some of the requests. Let's go back to the terminal and create some heavy traffic here. As you can see, v3 is also in our graph now. There are different graph versions here. Some show them grouped as services, some show them grouped as workloads. Let's check istio virtual service config. Here on the right, you can see the new weight distribution. If you click hosts, you can also see the overview of the hosts. Well, in this detailed graph, it will give us some more information about weight distribution. As you can see, Reviews version 1 traffic is almost 3 times more than version 2 and version 3, as we've configured it. Now, let's try the example we used in the lecture. Let's try to distribute traffic by 99% to 1%. Yes, version 1 and version 2, okay. We can remove version 3. This probably will take some time. Okay, we've waited a bit, and as you can see, the weight of reviews version 1 traffic has changed drastically. And it will probably change some more over time. And also in the browser, we cannot see the second version, almost at all. Ah, there it is. Now, let's do another example. Let's remove the other destination. We want some of our users to see some specific versions of our app. For example, our product owner might have said, everyone has a non-star version, but for a special user group called CodeCloud, they want to release a starred version of our app, which is a very nice and rich feature. And let's add a new section under HTTP for that, called Match. When CodeCloud user signs in, they'll see the black star version, and the rest of the users will see the regular one. To do that, we'll now add a rule. This rule will pick the requests that have end user in the request header, and it will check if it's matching exactly with CodeCloud. If a request passes this rule, it will be routed to reviews version 2, and the rest will be routed to reviews version 1. But how do we create a request that has CodeCloud end user in the request header? Don't worry about it. We have a feature in our application. See the tiny sign in button on the top? That's for adding an end user header to the request. We'll just type our username and write a random password, then sign in. There's actually nothing this app does in terms of checking this user. It is just for experimenting with request header. Once you sign in, you'll see the reviews version has changed to version 2. And it is not related to a weight distribution rule at all. I keep refreshing, but the page is still the same. However, when I sign out, it changes back to version 1, just as we configured it to do. Now, we are happy with this, but we also want to introduce a new version for a specific group of people, and we want them to test it, and they can even give us some feedback. For this, let's create another match section and give a very secret name to these users as test users, okay, and route that traffic to our newest very colorful version, version 3. As you can see, the bar on the right shows both three routes are 100% in weight once they've matched our rules. Now, let's try the default version without signing in. Yes, it's a no-star version, version 1. Let's try if our new version is available to test user. It is working and there is nothing else test user can see. And CodeCloud user is still seeing the black star version with no problem at all. Virtual services are powerful, and as we've just experienced, they can help you manage your traffic with much flexibility. In this demo, we'll create some different subsets using destination rules, and forward our traffic to those service endpoints grouped together. Before that, let's have a look at our existing destination rules for reviews. We have 3 different subsets, and they refer to the labels as version v1, version v2, and version v3. Here in the virtual service, we simply use these subsets to route our traffic. But what if one day we somehow needed to group different deployments together underneath the same service with a different rule or label, let's say? To do that, first we need to add a new label to our app. This new label will help us create some different destination rules. Here, I copied the reviews YAML from the samples directory. First, I'll add test beta label to review service. Then, I'll skip my first deployment because I don't want the version v1 in this new grouping, and add the same label to version v2 and version v3 deployments. Now, we'll delete and then apply this YAML. Now, when we go to the KLE dashboard, our labels can be found in the workloads page. Here we have test beta in version v2 and version v3, but not in version v1. So, also in the applications page, you can see our service has the new label already. Now, let's go to istio4 and create our new subset in the reviews destination rule. Let's keep version v1 subset and add a new test beta subset. This could help us test new 2 different versions of our app. Like, we can even ask which one they prefer to our customers. When we go to the virtual service, because we just removed our old subsets, KLE is warning us with these yellow lines. Let's only keep v1 and only add our new test beta subset as a single destination together. Oh, we also need to tell how to manage traffic between those. So, let's open our app to only 10% of total traffic. Obviously, I need to put the name of the subset here and I got it wrong. Let's go back to our destination rule. Yes, it needs to be test. If we go to our browser, we'll see reviews version 1 most of the time, and version 2 and version 3 shows up, but rarely. We can create some traffic to see how our app is doing. In istio4, we can go to reviews and see the traffic distribution. Version 2 and version 3 almost have the same weight, but version 1 is almost 9 times of their total. Now, let's change this weight distribution altogether and see how our app is doing. Here, version 2 and version 3 are taking over the world right now. We then can also create a traffic policy for test subset, and it can be a random load balancer. This way, we can distribute traffic randomly in our subset. As you can see, reviews version 2 and version 3 started to change randomly. Now, we can all delete these subsets and try a different traffic policy. It will make all our review apps work in a round-robin mode. We also need to remove the subsets from our virtual service. In the browser, you can follow that the review service is changing in a round-robin mode. Destination rules, in conjunction with virtual services, help us configure complex traffic management policies. In this video, we will talk about fault injection. So, here is what we have done so far. We have deployed the application, configured a gateway, set up the product page virtual service, and the reviews virtual service. And it's all working as expected. Next, we would like to introduce some errors to check if error handling mechanisms are working as expected. And that is fault injection. This is a testing approach, and it helps us to see if our policies run efficiently and are not too restrictive. We can inject errors in our virtual services, and these could be two different types of errors: delays and aborts. In this example, we are injecting a delay type of faults in the mesh for ratings virtual service. Since it's described as percentage, it will add a delay for 10% of requests, and this delay is configured as 5 seconds. Apart from delay, you can also configure abort to simulate errors by rejecting requests and returning specific error codes. For our fault injection demo, we'll introduce a delay to our details service. Let's see how that goes. Before creating the fault injection rule, first we need to create a destination rule so that we can have a subset for this rule to work. Then we will create a virtual service. Let's give it a name as details and add details in the host section also. This virtual service will be affected details service. Then we'll add a fault section under HTTP protocol, and this fault will configure the delay we're about to introduce to our service mesh. Let's say our 70% of traffic will be delayed for an extra 7 seconds. And I'm using the details subset v1 destination for this virtual service to be routed. Let's save this file and exit. We can now apply it with kubectl apply. Yes, it's created. To test our fault injection, we'll use the curl loop again and then switch to Kiali to see how this delay affects the whole mesh. First, let's check if our istio configuration is valid. Yes, they're here and they have the green checks. Now, we can go to our app and follow the fault injection there. We've already started having some issues with detail service here. As you can see, there's a red arrow going out of product page into the details, which is not looking very healthy. And also, there's another arrow, a green one, showing that some of the traffic to details is still looking good. If we go to our browser and refresh it, we'll see that details cannot respond in a timely manner because of our fault injection. If we keep hitting refresh, we might get one of the 30 of healthy traffic, so let's try that. Yes, every once in a while, we can get a response from details. So, with this fault injection, we understood how our product page would respond if one of the services starts slowing down. By using this technique, we can configure how our mesh can work in a coordinated manner. And we can understand our services' strengths and weaknesses one by one. Let us now talk about timeouts. When it comes to software, we must know that anything could happen. Since each service within this microservice architecture is a software, we should expect them to slow down, fail, or go completely crazy for no obvious reasons. And since the services are dependent on each other, slowness on one service might affect the other services dependent on it, and even have a cascading effect. For example, if the rating service slows down for some reason, we will have requests queued at it, which is going to cause requests on the review service to be queued up, which is going to cause the requests on the product page to be queued up. So, let's say, for example, the details service slows down. Then the requests coming from product page to details service is going to get queued up, and the request to product page itself is going to get queued up, affecting all users accessing the application. That's why we need timeouts. If a service is taking too much time to respond, it must not keep the dependent service waiting forever. It must fail after a period of time and return an error message. That way, the dependent service gets an error message and is not impacted. That's what a timeout is. We can either configure a timeout at the details service for it to fail, or we can configure a timeout at the product page service for it to fail sooner rather than waiting for the details service for eternity. So, here we have the details service and the bookinfo service that directs traffic to the product page. We want to add a timeout to the product page service to reject requests if it takes more than 3 seconds. For this, we add a timeout option and set it to 3 seconds. Now, since our app is working perfectly, how do we test this? Because we don't have that much traffic and our details service works perfectly. We want it to fail. That's what we learned in the previous lecture. We could simulate a failure using fault injection. For this, we add a fault section to the details service with a fixed delay of 5 seconds, and we inject this failure for 50% of the traffic. Well, that's it for now, and let's see this in action. To be able to try a timeout, first we have to force one of our services to respond slower. We'll do this by injecting a delay into our mesh. Then we'll create a timeout, so our mesh will work cohesively, and our services will not have to wait for so long, even just to get an error message. To make this timeout definition visible, let's introduce it to the product page so we can see it on our browser. Here is the virtual service we'll use to introduce a delay. This means Istio will have the details service wait for 5 seconds before returning a response for 100% of the traffic coming in. Let's apply this. When we try it in our browser, you can see the details service is throwing an error. Let's try decreasing this percentage to 70%. Now, we have the details sometimes, but most of the time it fails. Okay, so with this configuration, if the details app takes more than 3 seconds to load, the product page itself will throw a timeout. Let's also lower down the 70% to 50%. Now in our browser, when the detail service is not responding in a timely manner, we started seeing the timeouts we configured. You can use timeouts when services are dependent on each other, which is mostly the case in microservices, and when you want to make clear definitions between those dependencies. Let's talk about retries. When a service tries to reach another service, and for some reason it fails, we can configure the virtual service to attempt that operation again. This way, you don't have to handle retries within the application code. You can configure retry settings, which basically says the number of times to try and the interval between them. Istio by default has a retry behavior which is 25 milliseconds between retries and retrying 2 times before an error returns. Let's examine a retry setting. Like timeouts, retries are also specified on virtual service level. You can set the attempts to try before it gives up and returns an error. And you can set the delay between each try as well using the per try timeout option. Let's now look at circuit breaking. We know that the product service communicates with other services, such as the reviews or the details service. If, for some reason, the details service breaks or slows down and is unable to serve the product service, all requests from the product service will pile up at the details service, essentially creating a delay as the product service is waiting for response from the details service. In such cases, we would like to mark the requests failed immediately as it is sent to the details service. This is known as circuit breaking. This allows us to create resilient microservice applications that will limit the impact of failures or other network-related issues. The same is true if we would like to limit the number of requests coming to the product page itself. Circuit breakers are configured in destination rules. In this example, we limit the number of concurrent connections to 3 on the product page destination rule. Let's head over to a demo and see this in action. Now, let's create a circuit breaker to prevent our services going down when they are under high load. For this, first, let's remove all the subsets from our product page destination rules and virtual services. Then, let's configure our traffic policy with some strict rules. In the HTTP section, we are telling Istio to limit the maximum number of connections to our service to 1. With HTTP 1 max pending requests, we are defining the number of requests we'll keep on waiting if our service is busy. The rest will be denied. So, max requests per connection is also telling how many requests our service can handle per connection. Now, we've limited all those. Let's try it with a tool called h2load, which will also be helpful in creating concurrent calls. So, -n here shows the number of requests and -c number of concurrent clients. Let's try 1000 calls to product page service. So, Here in H2 load, we can see the progress by percentage. And yeah, so it's finished. It says, all our requests were successfully handled by our service. Amazing! Let's push this a little bit more. Let's have two concurrent clients. So, if our service hangs with one request, the rest will be denied. Okay, we only have 14 requests denied here. Let's try increasing the concurrent client to 3. Now, more of our requests are being denied. And with 4 concurrent clients, our service can only handle 46 connections with this rule. Here in Kiali, in the graph view, you can see that the product page has started to fail because of our very strict circuit breaker. It basically cannot take many of those requests. A/B testing is a very popular and powerful approach to understand user behavior. It boosts experimentation and helps us software professionals to not guess how our applications will be interacted, but to see it on real data. We have seen this already in the virtual service topic earlier. With Istio and virtual services, we can now create a virtual service instead of a service, and we will call it reviews. We then define two destination routes for traffic distribution, subset V1 and V2. And we set a weight for each, 99% for one and 1% for the other. Now, we can route 99% of traffic to one service and 1% to the other. Even if the reviews V2 service had 3 or more pods, the traffic distribution will still be 99% to V1 and 1% to V2. The number of instances now has nothing to do with the traffic distribution, and we can easily control that through the virtual service configuration.